Swayam Prabha. Digital India. Educated India.
Okay, know this. What is del square? Anyone knows what is del square? It is basically the second order derivative. Okay, in 3D, it is second order derivative written in 3D, 3 dimensions. The 1D version would be second derivative with respect to any coordinate, like if this acts on the function psi, then this is the 1D version of del square of this function psi. Psi itself is a function of position. It's usually a function of position and time. Here I have simply written this in terms of an equation without time. Okay, so this is the governing equation. What this tells me is that if I want to know anything about the hydrogen atom, just as for the trajectory I need to solve Newton's equations, here I need to solve this Schrodinger equation. Yes?
Does this equation have something to do with the h psi equal to E psi?
So H, yes, you have E psi on the right hand side. So the left hand side can be written as H operating on psi is equal to E psi. Okay. So for example, then I would have to write H to be, but that is just some, I did one push up, right? Suppose I say H is plus minus E square by R. If I define this to be H, then I can write this down as H psi is equal to E psi. E is basically a number, and this is what we call an operator. There have been operators in your life other than cable operator or whatever operator, right? Machine operator. This is an operator. What do we mean by the operator? This del squared, we say acts on psi. But the math is, I'm not going to teach you quantum mechanics, not in the next 5 minutes, which is all the time I think I have. Point being that this is the mother of all quantum mechanical equations and stuff. There are, more abstract versions such as the Hilbert space and whatever. But then we take this equation. Now, you know who this is on the chalkboard? In front of the chalkboard? Okay, there's a very famous physicist called Paul Dirac. Okay, he's the relativistic version of this equation is named after him, the Dirac equation. So what he said about doing physics is that I consider that I solved a problem if I can predict what happens to its solution without actually solving the details, which is the approach I'm trying to advocate here, right? Yes?
Just two doubts about the notation, sir. In that Schrodinger equation you have given, the denominator for the second term, that's dot r.
Dot is not dot product, it's just multiplication. In the parenthesis here, I put parenthesis and dot. I've just retained a placeholder. If I had written this in SI units, this would be 4 pi epsilon naught. Oh. If I wrote this down in some other system of units, it could be 1 or whatever. It depends on the system of units, so I'm not bothering to fill it in. It would just make the equation look a little bit messier. The natural system of units to this In this case is called the atomic unit. Atomic units, there is something like that. You will learn all about it if you really take up physics, right? So let's
Also,
keep
one
it,
more, sir.
keep it to, take the math for what I tell you. If you don't trust me, check it up later on. Yes.
Sir, you have on the board. Why is there a triangle on top of the equal sign?
The hat, this is the hat. The hat is on top to designate the fact that this is an operator. How do I otherwise?
Not that one, sir. The on top of the equal sign.
Oh, this means definition. An equation is different from a definition. So you put a D or a DEF or a delta to say that it's a definition. Yeah.
Okay.
I'm defining H to be so. Anyway, as I said, take my word for it when it comes to the math. You're not going to solve all the math here. There are nice lectures online which you can learn about. You need to know a little bit of differential equations, have some skill with differential equations to do this. If you study any branch of physics or engineering, you are eventually going to learn some of this stuff. So please take it from me. But I'm going to adopt the spirit of Dirac and say, I would like to predict without solving it. I'm a lazy guy, right? All of us are lazy at some level. Why not? Or let's do that. So how do I solve this equation? What's my goal? I want to know something about time scales. My natural time scale is 1 per second. That's why we have seconds in the clock and whatever, right? The electron we saw in one model, it is 150 attoseconds or 0.15 femtoseconds, right? Now, what are the natural time scales that this equation puts upon us, right? I'm going to claim that you don't need to solve this problem. Just look at the constants in this equation. H bar, M is the mass of the electron, E is the charge of the electron. Psi is not yet known. I'm solving for psi. Okay, I'm going to solve for psi. E is another quantity which I don't know. I need to solve for E. Does the term eigenvalue resonate with you? The eigenvalue of so this is an eigenvalue. This is an eigenvalue equation. I operated on the function psi with some operator, a part of which is differential. It's del squared. It's a differentiation operator, twice second order differentiation operator. Operates on psi. This is multiplicative minus E square by R. And it spits out a number E and psi itself. I'm adapting this form of an equation and only looking for solutions, psi and E, which will come across this when I introduce H. Right? So that's the spirit in which we are casting this problem. So this is an eigenvalue problem, right? So I want to solve an eigenvalue problem. But the point is, I'm going to get some juice out of it. That what is the time scale on which the entire thing operates over here? Right? I can get a sense of it without solving the equation. How so? Let me take the constants in this equation, H, M and D, and construct and put them together so that I get a quantity which has the units of time. Have you done this for F equals Ma and G M1 M2 by R square? Right? On what time scales does the dynamics of the the sun-earth system happen? You can figure that out. You have force, you have masses, you have some distances. So you can approximately come to the fact that it is in seconds or hours or days or whatever. It's an exercise I would recommend you to do. So let's do that. Any time scale that emerges from this equation will have to have these three symbols in it. Yes? So I can construct a velocity from this expression by noting the fact that E square divided by H, okay, this is the definition of the velocity, not the definition, I deduce that the velocity essentially is E square divided by H bar, and this is equal to C by 137, as I told you. I know this from a little bit of maybe browsing or getting some details across, so be it. I take the velocity, I make it an energy by doing mv square. Alright, I took the velocity, E square by H has units of, H bar has units of velocity, and then I convert the velocity to energy units by squaring the velocity and multiplying by mass, because kinetic energy is half mv square. I'm not bothered about factors like a half or a 2 or whatever. I simply want to get, do the what is called a dimensional analysis. I want to combine 3 different constants and get this to become the dimension of time. So I got velocity, I got energy. That's nice. This is something which you may or may not know, but take it from me. H, Planck's constant, has the units of energy times time. It is joule second, right, madam? That's what you said. It's joule second. What is the value of Planck's constant in joule second? So H is, so she is helping me. Very good. H is 10 to the minus 30. So this is energy times time. So that's what I was driving at. If I can create an energy scale from HM and D, H is already in the units of energy times time. So I will pull out time by dividing H by this expression for energy, which I do. And I put in the numbers for H, M, E and epsilon naught in these equations. I have done the math for you. Then this T, this new time which I have constructed entirely in terms of H, M and D. These 3 constants. Okay. The DNA of the electron lies in H, M and D as far as the hydrogen atom is concerned. What else does the electron have? Nothing else. It can't own property, can't buy a car. Nothing, right? Literally. So H, M and D is all it has. Therefore, the time scale, the lifetime of the electron should be measured in units of 24 attoseconds for the hydrogen atom. So this T, by the way, 24 attoseconds is called the atomic unit of time. 1 atomic unit of time is 24 attoseconds. So you learned something new. So measure everything for the electron in these units, in units of attoseconds. That is why electron dynamics happens on attosecond time scales. Alright? An attosecond is related to the atomic unit of time, or I would say it's the heartbeat of the electron. The second is my heartbeat, your heartbeat, whosever heartbeat. And attoseconds are the time scales on which the electron's heart beats. Convinced? Now, this is a lot of math. I don't really intend to take you through a whole lot of this, but life is made up of molecules. Now, the point I want to make here is that, you all heard about the orbitals of an electron? Yes? Yes. Oh, you know a lot. You know the s orbital of the hydrogen atom. It's like, what's the shape of the s orbital? P orbital? So it comes about because these wave functions, right? When I map them in 3D space, I should do this in the coordinate system with r theta phi, the spherical coordinate system. So if an orbital is spherical, then this orbital or the wave function, basically it's the psi of the 1s state of the electron, right? This psi can depend only on r, it can't depend on theta or phi. Therefore, it's a sphere, right? A surface of constant r in SPC is, a surface of constant r in SPC is, in spherical polar coordinate system, a surface of constant radius r, radial coordinate is, so that means for those set of points, I've collected all those points and made a contour, and theta or phi doesn't matter. I've imposed a constraint, right? We are all such ants walking on approximately a surface of constant r on Earth. So we are living on an s orbital, right? Do you see that? We are all living on an s orbital. But if there was a theta or phi dependence, the shape of the orbital will change. So this orbital depends only on the azimuthal angle theta. There's a cos theta here, right? Everything else depends on r, whereas there's a cos theta. That's what gives it the dumbbell shape. Now, the point is, electrons live on these surfaces, okay? These are surfaces not necessarily in physical space, but in some kind of space, right? There are energies associated with this. That's a different matter. So now, what if I want or we want an electron to jump from this 1s state to a 2p state? We want to do this. Does it happen? It happens all the time in physics, chemistry, and whatever. When a photon enters my eye and something happens and I see it, this sort of a transition is happening. It's not in the hydrogen atom, but some kind of dynamics is happening. That's also a quantum system, by the way. So to make a 1s to 2p transition, we are now becoming, crazy after getting to know about time. Question I ask is, how much time or what is the time scale on which this transition happens? Electron living in 1s transitions to 2p. It's not a physical jump, by the way. Okay, it's not a physical jump. How much time does this transition take place? I can map that time. How can I figure out that time? Again, I don't want to do all this complicated maths. The trick is here. What is time in the quantum world? Time is Planck's constant divided by energy. So just find out the energy. What is the energy budget for this transition? That's all you need to know. Open up a handbook of physics and chemistry, look into Wikipedia, go into the NIST database, find out. The database will tell you that this level 1s is minus 13.6 eV. Why minus 13.6 eV? If you give this electron 13.6 eV, it will become free. That's the energy with which it's bound. 2p electron minus 3.6 eV. If you give it 3.6 eV, it will come out of the atom. Now I have these two energies, just take the difference, approximately 10 electron volts. So Planck's constant divided by 10 electron volts. Electron volts being a unit of energy, right? Now write Planck's constant instead of joule second, like my colleague here said, write it in the units of electron volts femtoseconds. Turns out to be 4 eV femtosecond. So this animation which I created on MATLAB is essentially showing the dynamics of an electron transitioning from the S orbital, going from the S house to the 2p house. It takes 400 attoseconds. It has to hail a taxi and go, right? This is the version of it. Of course, I'm kidding. The transition happens on time scales of 400 attoseconds. That's electron dynamics in a molecule. The electron has changed its configuration, right? So therefore, maybe, I don't know when I should stop. Who is managing that, sir? How much time do I have? Huh, sir? No, how much time? I can go all afternoon. No, they will not get lunch. 1 hour, but I came late. Is it? When is lunch, madam? Oh, so they will be cursing me. I'll take about 5 to 10 minutes if the class agrees. If you say no, we'll go for lunch, no problem. Sure, Arish. Okay, 10 minutes, okay? Not 10 attoseconds. It's too short for me. So, what's the lesson we learn, right? Let's ask ourselves this question. When electrons make transitions, an electron, whether you view it as something going around a Keplerian orbit, which is outright incorrect, but it is useful. We still use this notion to think about things because that's the notion we have about the model of the planetary system that we are living in, right? So it's not too bad. Trajectories aren't entirely useless. But then a more sophisticated learner would understand that it's actually wave functions and transitions. But it has all got to do with electron dynamics. If we now take this mantra of T, okay, being H Planck's constant divided by E, right? If we take this as the mantra of this world, the quantum universe, right? Then all I need to know is from the energetics, energy values, energy budget, from the energetics, I can figure out the time scales that are involved. right? So everything depends on H. So the energy budget of electrons transacting is electron volts. If I put 1 to 10 electron volts here, I would get that these times are in attoseconds. That's why electron dynamics is said to happen on attoseconds. Alright? But what else can happen in the atomic quantum world? What else can happen? Suppose I give you a molecule, H2. By the way, the calculation we did earlier was for atoms, but now I have a molecule like hydrogen. You are sitting in a chemistry department. So it's all about bonding here, right? Chemical bonding, not human bonding. But you're all from different schools, right? You probably didn't know each other earlier, right? But now you're interacting. You'll probably stay in touch, right? Some of you may become very good friends. Some of you may become mortal or immortal enemies. I hope not, but it's a theoretical possibility. Some of you will remain acquaintances. You may see that person in the airport someday, and whether you remember the name or not, you may recognize somebody. You may get acquainted, right? So there's a certain bonding happening. Know it or not, want it or not, right? So basically, molecules also can do that. I'm not trivializing it. There are various kinds of bonds. There's a type of bond that two hydrogen atoms bond together and make a molecule, right? Whereas two helium atoms will not do that. They will not form such a bond. They're like Sheldons in this universe. They interact very poorly with others, right? Others, hydrogen atoms are a bit like the pennies of this universe. They interact very well, if I may say so. But the whole point is, that's not the whole, I'm not trivializing it. How do I quantify this bonding process? There's an energy involved in it. We form a stronger relationship with, say, somebody, say our own sibling, brother or sister, right? Because we invested a lot of time and energy into it. That's what we say. Whether or not we are conscious about it. To make a new friend, you invest time or energy, right? If you don't like the person, you barely invest any time or energy, right? So basically the point is how much energy is involved in the bond, whether it is a chemical bond or a human bond, that's what matters. So if I figure out this energy, then I can figure out the time scales on which the dynamics of this bond takes place, right? So basically, if we have two atoms, they can maybe vibrate. Yes, they can vibrate, right? So that vibrational energy determines the time scale on which vibrational dynamics happens. So who studied vibrations of molecules? C.V. Raman, Chandrasekhar Venkataraman. He got the Nobel Prize for figuring out a spectroscopic method which can discern the details of vibrational dynamics in molecules or dynamics in condensed matter, right? Where they are called phonons and so on. Very clever guy. He did something very clever, which I don't have the time to go into today, but you have enough information online to look it up and understand that fact other than just know his name, right? So please do that. He was such a freak for vibrations. At some point in his career after the Nobel Prize, he started studying the vibrations of mridangam, tabla, Indian drums. So he has a book on studying the vibrations of musical instruments. He has a book on the physiology of the human eye also. Because he didn't have much more sophisticated detectors. He had the human eye and photographic plates to work with, not these cameras with a gazillion pixels to take God knows what, all kinds of images and selfies and throw it onto social media. God knows for what reason, but that's what we are doing quite often, right? But he didn't have all that. So vibrational dynamics happens on femtosecond time scales. You don't have to take my word for it. If you open a chemistry textbook, you would be told that the difference in energy between electronic transitions, E electronic to E vibrational, the ratio is of the order of 10 to the 3. This comes about by explicitly solving the Schrodinger equation. Now, likewise, so these energy budgets vary by an order of magnitude of 3, which is a factor of 1000. So, vibrational dynamics of molecules happens on the time scales of, on these time scales. By the way, one of the Nobel Prizes in chemistry, I think it was in the year 1995, was given for femtochemistry. Okay, you can look it up. Went to a Nobel laureate called Ahmed Zewail. Now, I'm going to ask you one more question and we'll probably close with this, right? Anybody made popcorn in your microwave? Who has done? Oh, put up your hand, put up your hand. I have never made popcorn, I've made other things. In your microwave at home. Only 4 people. Okay, anybody ate popcorn made in a microwave or any other? Are you sure it was made? How many of you had microwave popcorn versus movie theater popcorn? Okay, so you know that you can do popcorn in a microwave. Okay, but that's not the real question. The question is, how does a microwave oven pop the corn? Why does it pop the corn or warm my coffee? Or if I put chocolate, melt my chocolate? What? Microwave. Yeah. Such a trivial answer. So why? So there is, you have Wi-Fi? Yes?
Perhaps the microwaves transfer some energy to the molecules which get, they vibrate because of kinetic energy, they get heat.
So you have to say that in the mic.
Sir, so when we have some food item in the microwave oven, so the microwaves are passed and they transfer some energy to the food material. Therefore, the molecules or atoms, whatever, they vibrate and they cause kinetic energy which heats it up.
Your name?
Tanusha.
Tanusha. So Tanusha says you supply energy, it vibrates and then that's it. And food gets cooked. You agree? The man in the hoodie. Do you agree? You don't know. You're Pink Floyd. Okay. I don't know if there's a Pink Floyd song on that. I'll check it out. Yes, sir.
So the microwave oven actually just heats the moisture and not the actual food, and the moisture heats the food that is present.
So he says it's because the microwave interacts with the moisture. Moisture being?
Like water, liquid water or liquid
Water. It interacts only with the water molecules and they do something.
They have
to them.
dipoles.
They have dipoles. And then what happens to the dipole?
They like shift around and move here and there because of the microwaves passing, and they produce a lot of energy, and so that they heat up. Because they heat up, they produce a lot of heat around and they melt. Heat up.
Excellent
And
point.
also,
We are converging. We are coming to closer to the answer. Yes.
another thing, the kernels have moisture, like a little bit of moisture inside them, so therefore they pop. Like that popcorn. In the case of
Okay. Yeah. There is a lot of, then the chemistry takes over. Excellent. Yes, madam. Your name?
I am Thiruvengadachari. Thiruvengadachari.
Thiruvenkacharam. Your name? Huh? Adavan. Okay. And please spell out your name just so that we talk to people.
I'm Ananya.
Ananya. Okay, Ananya.
So I have a question.
You're supposed to first give me an answer. How do you make popcorn in a microwave? That's the most important question, not what are attosecond pulses.
No, not about this, sir. Like related to the microwave question.
Yes.
Sir. So does that microwave excite the electrons?
I thought you would know something about it.
I didn't know.
She said vibrates matter. Yes. Tell us your name and share your comment.
I'm Vaishnavi.
Vaishnavi,
The
yes.
electromagnetic waves have oscillating electric fields.
My coffee is cold. I need microwave to heat it.
So the oscillating electric field will influence the dipole in its to change in its direction. So the dipoles get oscillated back and forth with respect to the electric field.
Excellent point. All of you are partly correct and I take all your answers, but I don't have any prize to give you. Right? But you're all grown-ups. You don't need any prizes. You just have a board exam waiting 12 months from here. So you better learn to work without prizes. Right? Sorry, I'm getting a little too edgy on, making you get a little too edgy on that, but maybe your parents will be happy that someone is doing it on their behalf, right? So anyway, that's a great point. But. The Wi-Fi router in this room operates at approximately the same frequency as your microwave. Are you not scared about it now? Shut it off. It's cooking you and me slowly, but definitely. Should we all not be worried about it? Have you not heard those 100 scary stories about why food cooked in a microwave causes I don't know what disease? Some terminal disease it is usually, right? That's what some YouTuber is telling you all the time. So are you all going to agree to the fact that the Wi-Fi router, apart from connecting me to the rest of the useless world or sometimes useful world, is doing it, but also cooking me, you, and making us all edible things for what? God knows. Are we really getting cooked? It's popping corn. You said water. We are some 80+% water, if not more. Yes.
Sir, perhaps because it has to be directed at us, maybe it's a big.
Sunlight is not directed at us. Are you saying now I can walk out and feel as nice as in this room? Right? It's just about absorption and emission. Okay, I'm not going. Yes, sir.
Sir, is it because the microwave has some reflecting material which just keep the microwaves inside and not lets us out?
Do you think we have reflecting material painted?
No, sir, like
well, you can put some absorbing material called a sunscreen when you go out. So, do you have microwave screen every morning to apply after a shower? Does anyone do that? I have not done it. So maybe I'm vulnerable. You are not. So what's the deal? Why is microwave not cooking us if it's not cooking
Sir,
us?
is it the concentration of the waves?
Concentration. That's what I'm trying to say. Yes, it's diffuse, but so is sunlight. It's fairly diffuse. The point is, just because there is electromagnetic radiation, it doesn't mean that it always will cook us and make us edible, more and more edible. No, we are not suffering through that. There's a reason why a microwave operates the way it does, and for example, when I put my cup of coffee in the microwave, it heats my coffee, and you should not put metals in it. Someone told you so. It doesn't heat the ceramic, the container. Have you noticed that? Not at least as much as a flame stove does it. Have you noticed that? So it's not that just because there is microwave, it's going to cook the hell out of all of us. Even there is some material which isn't getting cooked. So there is something specific to it. Find that out. But I will tell you, for just cut short my story and tell you why a microwave cooks the food. Yes, it does. It interacts with the water. Water has to primarily absorb microwave. Right? Does water absorb sunlight? Yes, but does it absorb sunlight as much as a black cloth? No, it is. If it did, it would be black in color. It absorbs all light, right? It's not. It is transparent, so it absorbs a bit. Also, pure water will absorb very little of sunlight. It is fairly transparent, although radiation is interacting with it. But if you want water to absorb radiation, then you must go to the right frequency of the radiation, right? If you use radiation of the right frequency, water will absorb. If you use microwaves of the right frequency, water will absorb those microwaves. What do we mean by the right frequency? What do we mean by the correct frequency?
Sir, before that, because you said
No, first let's stay here. Then I'll come to your other one. What do we mean by the right frequency? Yes, what is the right and wrong about it? Is it written in the constitution of atoms and molecules, or what? Who determines that? So the answer to that is the fact that if I have the 1s 2p, if I have two quantum levels, the system absorbs energy, okay, only if you know this. You know E equals h nu. If this is my E This is the given E in the system which comes about solving this eigenvalue equation. This nature gives you. This is like the time period of a pendulum. Square root of L by G. Eigenvalue, that's also like an eigenvalue. So is this. I get this eigenvalue, then I come in with the radiation. I input a radiation with frequency nu. Only if these two match. And when they two match, what is it called? It's called a resonance. Only if you have resonance, you will have absorption. So, that microwave radiation is resonant with something that has to do with the water molecule. What is that for the water molecule? Is it electronic transition? Is an electron from the hydrogen of the water molecule going from its 1s to 2p? No, 1s to 2p is about 10 eV. Microwave is gigahertz. It is micro electron volts of energy. Is it vibration? Maybe. I think Tanusha said vibration. Could be vibration. No, vibration is the culprit for global warming. This is what happens in carbon dioxide and why we are cooling the room and warming the globe as doing both simultaneously, right? That's because of vibrational energy, right? That's why we want to capture carbon dioxide. You know about that, right? And do stuff like that, which I don't think is working by any stretch of imagination. But why we popcorn is because this microwave does something really cute to the molecules. It makes the molecule rotate, makes the molecule dance. It's because of the dance of the water molecule that you are having popcorn, not the jumps, not the vibrations. Water does have, as you can imagine, 3 ways of vibrating, right? It's very easy to, it is H2O. So the two bonds can flex like this, they can bend, and the two bonds can symmetrically vibrate. The two H's can go in and out from the hydrogen, and or as your gym instructor would have you do the other exercise, it could be that one stretches, the other comes out. This is called asymmetric stretch of the bonds of the water molecule. So these are vibrational modes. But what is making the popcorn is water is rotating. It's dancing. Literally it's dancing. You can calculate the frequencies of, you can easily determine these energies. Right? Again from using HM and D. The mass of proton, here use the mass of the proton instead of the mass of the electron and calculate the vibrational energy. You need to know the distance between the bonds for water. It's a very nice exercise. Again, as I said, if you don't have to write the board exam, this is fun. You take these masses, you know these distances, or even if you have to write the board exam, it's fun. If you do it this way, you will not feel the pain of preparing for an exam. It will be fun. You have the bond lengths, you have the masses, try and compute the energy, right? Likewise, if the same molecule has to rotate, what would you do? This is my axis of rotation. I have to calculate the moment of inertia, I, for the molecule. Replace that with M, H, I, and E. The moment of inertia and do the math. You will get the fact that you will get a certain energy. Convert the energy to frequency using H nu. You will get rotational frequencies. And then you can set the microwave to the right frequency. That's why we have microwave ovens and not infrared ovens for cooking food. Infrared would have heated everything. This is a very efficient way of heating. You put in little bit of energy, make sure it's absorbed very well by the water molecule, and then it is cooking. So cooking on a microwave is more efficient and better for the planet in that sense than cooking on gas and heating everything. The vessel, the this, the that. If you have an AC in the room, you can see that radiation is coming out of that also. Anyway, that's for food science. I'm not here to do food science, but it has a characteristic time scale. That is, rotations happen on picosecond time scales. Vibrations happen on femtosecond time scales. And electronic motion happens on attosecond time scales. The point is, if you have light pulses, you can take snapshots of dancing electrons. Okay, now my entire thing is gone, doesn't matter. Stroboscopy, right? You can use flashes of light to make pictures of moving objects. These objects are moving very fast, attoseconds. So you need camera flash to be very short. So you can do that. So that is why the citation read that electron dynamics could be captured. But what you can capture in this world, you can also possibly control. When microwave was absorbed by the popcorn, you controlled a chemical reaction using photons or light or electromagnetic waves, right? So likewise, maybe you can control the dynamics of electrons and achieve some new technology with it. Remember this one thing, if technology is like a building, like skyscrapers in a city, science is that act of clearing the field on which technology can build. If you did not know science, you could never have done technology. If Queen Victoria, the old Victoria had told, bring me some device so that when I do my man ki baat, that device will put it in every home. When I speak, everybody should be able to see my video and audio, and I want such a device to be put in every home, I'll give you a lot of money. In her era, nobody would have been able to do it. Nobody. Why? Because then people didn't know that electromagnetic waves existed. The science for that had to be put in place, and then hell breaks loose. Now you cannot, if the same queen were to be alive, she would have found it hard to get herself out of every home. It's impossible. Every day people would have been seeing or listening to her like people see, I don't know, public figures and celebrities. They coexist with us in our homes, right? You put on that idiot box and you start seeing it. Or sometimes you don't even need to do that. These phones start doing things, right? All the time. So really, it's all boon or bane is for us to decide and use. But you need fundamental science to clear that field and enable this opportunity. In that sense, fundamental science in which society invests so little has already paid for itself multiple fold. So therefore, this kind of curiosity-driven research is something that we must continue doing as mankind, as Indians, as students of these schools and RSIC. With that, I'll take Adavan's question and we'll close. I'm going to allow you to go for lunch if that's your question.
If microwaves and routers emit radiation of similar frequency, how do we not get heated up? We said we don't, but
it's not exactly the same. They have taken care of that, luckily, right? So you can go close to a router and not be cooked. Yes.
Sir, you said that food, we all read about food being cooked by the microwave is not really healthy. So why is it so? If it is only turning the water molecules, how can it possibly affect the food and make it bad for us?
So last question, I will let one of you answer. Tanusha asks, it's all becoming about food. I can understand why. But yes, but the hunger for knowledge sometimes is supposed to be greater. No, I think so, but you still shouldn't do it on an empty stomach. Tanusha says, if your microwave only heats water, how is it cooking food?
No. Why is it making the food not very healthy? They say if you reheat and microwave repeatedly, it's not good.
Well, that's food science. Actually, it's a lot more complicated and messier than physics, which is why I stuck to this. Okay, the point is, it's about nutritional value. You must ask whether the micronutrients in the food survive this. It's a debatable topic. I don't want to pass any verdicts on it. I think any food cooked multiple times through any means is probably not as healthy. Any food stored beyond a point is probably not as healthy, and so on. So there are experts whom you can listen to, but trust me, just like in physics, the best thing about physics is you can cross-check everything yourself with a few numbers. That you can't do in every science. But in the other sciences, do that. That's the lesson you should know. You will be able to verify stuff in other sciences. You must do it in physics. It's very easy. Few numbers will do it. So that's my message to you today that this is all there is to attosecond physics to give you an invitation. The rest you're going to explore in the time you have. So Don't stop thinking about attosecond physics when we stop here. Please start thinking about it. That's all I would say. Thank you for your attention.